All right, ladies and gentlemen, we have a little bonus video for you here today. With our probability unit coming to an end, I thought doing a little mini review before the review would be nice. So you've had the option to grab this in class. This isn't a video we're going to go over in class. We'll do the total review for that. But this is something for those of you that think you need a little extra something to be able to help out with some of the issues. So I sincerely hope this is helpful to you. So all right, number one. A number 1 through 30 is randomly selected, followed by a letter from the word target. What's the probability of choosing a perfect square? Okay, that's my first job. Then, the letter T. Now, first thing I notice is, these are independent from each other. Meaning, picking a number and then grabbing a letter out of a word, they have nothing to do with each other, so they're separate things. We're going to be multiplying their probabilities together. So, first, in a number 1 through 30, choosing a perfect square. Maybe it would be a good idea for me to list those. Okay, those are the perfect squares between 1 and 30. So it looks like there's 5 of those out of 30 choices. Then, choosing the letter T out of the word target. Well, there's 6 letters, and I'm choosing 2 of them. And then you just multiply across. And even if you just get to there, I'm fine with that. But, with our calculators, a quick math enter really isn't going to be tough to get it down to its most simplified form. But that's what we're doing with our general compound probability, sort of like we talked about a little bit last week for a couple of the days. So for 2 through 4, we have a basket that contains 8 green apples, 11 red, 5 nectarines, and 12 oranges. Mark randomly chooses a piece of fruit, eats it, which of course then I hope means it's no replacement, because it's going to be kind of gross otherwise. Then that's another, find each probability. First thing I'd want to, so as we get our grand total of fruit that we have here, let's see, 19, 24, total of 36 pieces of fruit. Probability of choosing a green apple, there's 8 of them, there's 36 total pieces of apple. Then a nectarine, but remember, Mark ate the apple. So now there's only 35 pieces of fruit left, and out of those there's 5 nectarines. So we do a little multiplying here, and then a little math enter to get to our simplest form, and we're good. Probability of getting 2 oranges. Okay, there's 12 oranges at the start, 36 pieces. Mark eats the orange. Now there's only 35 pieces of fruit. But notice he's eating the same piece of fruit. There's no longer 12 oranges. Mark just ate one. So now there's only 11. And you sort of start to see little words like eats it or puts it back in the bowl make a big difference when it comes to these. Then finally, the probability of a nectarine or an orange. Now we talked a little bit about this too recently. Or means when I'm adding the probabilities together, not multiplying them. So here, probability of a nectarine would be 5 out of 36. Okay, or an orange, not and. So it's not like one of them was eaten. So then I just take my orange, and lucky me, there's a common denominator, so I don't have to mess with this. And I just add those numerators up. And I'm ready to go. Okay, so words make a big difference. Or means plus. So as we move down a little further, 2 dice are rolled. What's the probability that the sum of the dice is at least 5, given 1 die is showing a 2? Now I know most of the time we see the word given and we're thinking about the big fraction thing. But let's think about this for a minute. 2 dice are rolled. Sum of the dice is at least 5, knowing that 1 shows a 2. So I want to say, here's my options. Here's kind of like how I may want to look at this. Because there's 6 sides on a die. So if I add all the possible numbers to it, the sum is at least 5. Okay? There's my possibilities where it would work. So, out of 6 possible rolls, because I could get any number 1 through 6, how many of them are going to be successful? 1, 2, 3, 4. Okay, A little common sense, a little logic. Excuse me. Okay, so for our next group, out of a group of 120 students that were surveyed about winter sports, 28 said they ski, 52 said they snowboard. 16 of the students who said they ski said they also snowboard. The students chose at random and find the probability. Okay, there's my slash bar. So here comes my A and B when I do my probability. So I've got the probability of skiing. And then up in the numerator, remember I'm going to have both. I'm going to have A and B. So skiing and snowboarding. All right. Let's see if any of the numbers are direct in the problem, or if I'm going to have to get a little creative here. Group of 120 students. 28 said they ski. Okay, so that one's good. And 52 said they snowboard. 16 of the students who said they ski said they also snowboard. Ski and snowboard. 16. Okay, that wasn't bad that time. A little math editor every time. But it's always A on the bottom, after the slash, or after the given. Okay. So now on the second one, I don't have the slash, but I see the word given. That's the same thing. That's like having the slash there. So, no snowboarding is my denominator. And no snowboarding, but we ski in the numerator. All right, let's see if this one's as straightforward. 120 students, 20 said they ski, 52 said they snowboard. It doesn't tell me how many don't snowboard, but I know there's 120 total, and I know how many do snowboard. So if I subtract those, that would tell me how many people don't. Now then when I get to the top, I've got to do a little more thinking here. So no snowboarding, and they ski. So the only thing I have that might help me here is 16 students who said they ski also said they snowboard. So if 16 do, and there's 28 that ski and 16 do, it means that 12 do not. You're like, wait, what was that one more time? Okay. 28 ski, but I want to know which ones don't snowboard. Well, I know 16 do snowboard. So if 16 say, yes, I snowboard, and there's 28 total, it means that there's 12 that don't. Got to think through this. Every single number is not just going to be sitting there for you on a silver platter every time. Okay, we've got to think that through a bit. So as we flip over, bag contains 3 red marbles, 5 green, and 2 blue. 10 total. Always like to have totals. 2 consecutive draws are made from a bag without replacement. They're taking them out of the bag and leaving them out. That makes a difference. Find the probability of each event. Okay. Find the probability of drawing a red, 3 out of 10, and then a blue, but be careful, the red one is now out of the bag. That doesn't affect the number of blue, but it does affect my total, because now there's only 9. And reduce that down. Okay. Probability of blue, then blue. All right, there's 2 blue ones out of 10. I keep the blue one that I just drew out of the bag. So now there's only 9 marbles left. Ooh, and to make it even better, now I don't have 2 blue marbles because one's in my hand. I only have 1 now. Details, details, details. Okay. Both draws are neither red or green. So not red, not green. What's that leave? Blue. Well, Harty. Both blue. Harty, it's the same one that we just did there. You're right. If you're paying attention, that can make it go faster for you. Okay, just a different way of wording the same thing. And then finally, D, the probability of red, 3 out of 10. And then be careful, not red. Okay, so green or blue. Well, I drew a red one, so that doesn't mess with my green or my blue. And I'm set. So you may notice as we start to look at number 9, it looks eerily similar. Same red, same green, same blue. Consecutive with replacement. I'm taking the ball I just drew and putting it back in the bag. What's that going to change? What that's going to change is, here where I had 2 out of 9 because the red ball was out, now it's been put back in, so it's 10. So the only difference, because look at all 4 of these problems were the same, the only difference is that second fraction now is going to have a 10 as a denominator instead of a 9, because I put the ball back in. I replaced it. So these answers will still be the same like they were before. And then my red, not red, just becomes 7 out of 10. And I'm set. Now when you see this, you will have actually seen some things with our sampling methods. And again, our sampling methods include experiments, where I'm doing something scientific, where I'm actually, doing something to somebody to see, how it affects them. Surveys, I ask people for their opinions. And observational studies, where I'm watching what somebody does, but I'm not changing something. I'm not using, giving one group a drug and not another group, or giving one group a study guide and not doing it. I'm just watching what they do and kind of taking note of it. So, on number 10, a reporter asked people leaving a movie theater to take a survey on whether they prefer television or movies. Identify the sampling method. Well, it's kind of obvious when the word's right in there. They're surveying people. Then state whether the sampling method has any bias. So if you want to know if people like TV or movies, and you just ask people coming out of a movie theater, is that biased? Duh, yeah. Okay, there's definitely bias because people at the movie I would think, like movies. If so, explain how the bias could be reduced. Where would be a place I could have my survey taken, maybe that isn't quite so obvious in how I want to do it? Maybe, I could do the survey at a mall or a grocery store and kind of see what goes on. And again, this is a chunk of what it's going to look like. This is smaller than the actual preview, so the preview is still your best bet, but hopefully you've seen this and kind of gotten a better grip on some things if you were having some issues before.